Good morning. Good morning, Mr. Körber. Good morning, ladies and gentlemen. Welcome to this ceremony, which I hereby open, and in which Mr. Körber will defend the academic thesis entitled Technological Advances in Mass Spectrometry Imaging. Before I will invite you to present a brief layman's presentation of about 15 minutes, I would like to introduce briefly again the supervisory team. First of all, Professor Heeren. And he's a professor of molecular imaging at Maastricht University, and Dr. Baluf. He's an expert in imaging, bioinformatics, and digital pathology, also at this university. Having said so, Mr. Körber, I would like to invite you to present your major results and conclusions to the audience in a brief presentation of about 15 minutes. The floor is yours.
Thank you, Mr. Prorector. I did my thesis in mass spectrometry imaging, which most of you know. You get mass spectra per pixel, and this is a really powerful technique with amazing potential to be used in a hospital, for instance, like for cancer diagnostics, because if you understand the local chemistry, you understand the disease. However, mass spectrometry imaging still is under development. It still has a lot of shortcomings, and in this thesis I focused mostly on two: sensitivity and throughput. Throughput is particularly important if you think about a hospital, because if your measurement takes many hours, it's not useful for a hospital where a doctor only has a few minutes per patient. And why is throughput in mass spectrometry imaging that slow? The reason is that it's operated in a microprobe mode setup in which you scan each pixel sequentially, one at a time. And this is very slow. Like the fastest instruments to the market, they can do 50 pixels per second. But if your image consists of millions of pixels, you will take hours. Now, on the right, I'll show you a different technology, and this is just my smartphone camera. This is a much faster imaging device. And why? It acquires all pixels at the same time. And the question now is, can we do mass spectrometry imaging maybe more like a smartphone camera and acquire pixels in parallel? And there exists a technology or an idea to do that, which is called mass macroscopy. And this is very similar. You shoot with an ion gun or a laser onto a sample, but you analyze and ionize a much larger area at the same time. So you have an image on your surface, but all you then have to do is lift it into vacuum. Then you have two ion optical lenses that magnify this image. This is completely like a light microscope, and the rest of the spectrometer is just there for a time of light separation in which ions of smaller mass to charge will arrive earlier at a detector than heavier ones. Now, this approach has been commercialized exactly once, to my knowledge, and it was a complete failure commercially because, you need a detector at the end. That is a camera, spatial resolution, but it needs nanosecond time resolution. And back in the 90s, with this instrument that we're still used today, this was not available. However, for completely different reasons, people at CERN, I don't know exactly why, built a detector chip with 1.5 nanosecond time resolution, Timex-3. And with this, all of a sudden, we can work. We can make this approach viable. So we linked up this Timex-3 camera with this mass microscope. We do a lot on the data side, but for you important to know is that all we do is basically we keep firing an ion gun, we move around over a sample while recording with the Timex, and then we add all the events we see in a huge image frame together. And this now is very, very fast and powerful, as I'm going to show you here. So on the left, you see an image of the fingerprints of a colleague of mine over a half slide. This is a very big image consisting of 1.2 billion pixels per second. If you do this with 50 pixels per second, you will still be here in 2 months' time. We did this in about 33 minutes. So it's a huge improvement in speed. On the right, we looked at a rat brain, for which we went a little bit slower to emphasize molecular detail, and we get very beautiful spatial information for, let's say, cholesterol. On the right, this is just potassium. We can do multiple zoom-ins. We have a high spatial resolving power and high speed. And this is a very powerful approach. However, there's no free lunch in science, and this approach has disadvantages. And I will talk about these shortly. So there are 3 disadvantages. The first thing is the detector sensitivity was rather poor compared to normal CCDs. I'll explain it more in just a second. The second thing, as this graph here shows, is that our mass resolution here was rather poor compared to conventional microprobe mode mass spectrometry imaging. And the last thing is this proof of concept was done with secondary ion mass spectrometry, which uses an ion gun. This is good to look at elements, small molecules and fragments, but it's not that good to look at large biomolecules of greater clinical relevance, for instance, lipids, peptides, and so on. So, and I'm going to address all of these points now. So I first will look at our detector, the way it is built and works. So we have an ion, a single ion hitting a DMCP detector, which creates a lot of electrons. This cloud hits a scintillator, and the electrons are converted into light, which we then measure with our Timex-free camera. We cluster and centroid these to have basically one event per ion hit. And this is how we do imaging on the detector side. And I want to talk more about the scintillator material here, because the scintillator does not emit light instantaneously. It rather emits it over a rise in a decay time, as this graph here schematically shows. And if this is very broad, then yes, your time resolution of your detector is not very good, and your mass resolution will be bad. And the scintillator we were using all the time for about, I think, 30 years was a P20. These are really good for night vision goggles, but only a small portion can be detected with the Timex-free, which is not good and explains our poor detector sensitivity. Also, the small portion has really long rise and decay times, so we did the very obvious and just got rid of this scintillator and exchanged it with an experimental one. We asked the manufacturer for one with extremely short rise time and very high brightness. And now what we see on the Timex is like a difference between night and day, like with the P20. This is supposed to be a horizontal slide edge, and you cannot see that probably. And now with a novel scintillator, we see beautiful images immediately. So we have a huge boost in sensitivity, and this is very important because all work since our 22 paper, basically, whether it's going faster or getting high quality data, builds on that. Now, the time resolution of our detector setup is also better, but it's not fully where we want it yet, because the scintillator still has a decay time component that we erroneously had hoped to get rid of via clustering and centroiding. We didn't. We subsequently developed an algorithm that gives you a narrower peak shape here in blue. The way we did this is we weighted clusters by cluster size and a pseudo intensity, and assume that it will be maximum at this point of the graph, and we will put less emphasis on later arriving photons. This curve is still 3.5 times worse than a waveform you get without spatial information from a DMCP, but it is a huge step forward nonetheless. And I'm going to show you this here with mass spectra. At the bottom you see one of the fingerprints, and these peaks are very broad. You cannot resolve many individual species. On top, it is now massively improved. We essentially have unit mass resolution in this Regis area. And this is, in my opinion, already important if you think about applications. If you want to, for instance, do elemental SIMS analysis at high throughput, you can think of semiconductors, but you can also think of biology applications that are targeted and make use, for instance, of length-finite isotopes to tag proteins with antibodies. And we can now resolve isotopes, so this is a potential application. For molecular analysis, I think we still need to improve. And for that, one should investigate using shorter decay scintillators, which now enter the market, like this one, that I think one should try once this is possible again. Okay, another thing is, we want to look at large molecules, lipids and peptides. And for that, SIMS is inherently not well suited compared to other techniques like matrix-assisted laser desorption ionization, MALDI. And in hindsight, that's a very challenging idea to do, because you use a laser, not an ion gun. And with each laser shot, you create orders of magnitudes more ions. To make this worse, this laser looks like this. It has a Gaussian beam profile, which means all of your ions will be in the center, and ions repel each other, and we never got anywhere with a Gaussian laser beam. We subsequently launched this beam into a fiber for multimode mixing to get a flat top laser beam, which is supposed to work better. But these flat top laser beams are very difficult to work with because they decompose when propagating through space, and that makes them not useful. So in the end, what we ended up doing, this is a CAD drawing of our vacuum chamber. And initially the vacuum chamber was here with a window and all the optics outside. We put a reentrant viewport into most of this chamber to have all the optics here, still pressurized, but inside what used to be the vacuum chamber. I like to make the joke that we shrank a vacuum chamber. And with this, we can do LDI and MALDI. So we first did laser desorption ionization without a matrix, because that's creating less ions and is simpler. This is a TM grid of a crystal violet dye, and 20,000 pixels per second is faster than the 50 of the industry. I think this is already very good, but when we do MALDI, this is going to fail spectacularly. This is also a TM grid, and it looks like a sun, essentially. Like you have rays everywhere. It's probably the most beautiful failed experiment that I've had. And yeah, it's not what we want, but all these rays, they point towards ions being deflected, and that means there must be an uninvited electrical field somewhere that's causing ion deflection. And we did some thinking and thought, okay, since we're doing imaging from insulating surfaces, maybe we're charging up the surface. So we repeated this experiment under exactly the same conditions, but we added a gold coating on top of everything to make the sample conductive. And all of a sudden it looks like this. We now can do all the imaging very, very fast. We see now very nice features of chemicals beneath this TM grid. We also see chemicals above the TM grid. 8,400 pixels per second, that's very nice in throughput. And this was very puzzling at the time, especially if you look at the mass spectrum, because we also got 2 orders of magnitude higher ion yield with gold coating than without. And if you look at the ionization process with MOLDI, gold coating does not enhance the ionization. In MOLDI, certainly not to that order of magnitude, and we were really stunned by this. In the end, we looked a lot into the literature, and we found that what is known is that you alter and broaden the kinetic energy distribution of your ions when you have surface charging. On a linear TOF, that means your mass resolution is going to be worse. Now, our instrument is a little bit special because it makes use of these electrostatic sector analyzers. And the radial motion of an ion through an ESA is dependent on kinetic energy. If you change that parameter, you will deflect, which explains the rays we see in the sun image. Or if you deflect too much, these ions are not going to pass through an electrostatic analyzer. So while these are very important for imaging and time-of-flight corrections, one could think about future instrumentation to use something else than ESAs. You could also think about enhancing charge compensation because there's still a lot to be gained there. But okay, that is about fundamentals. What about tissue imaging and lipids? Because that's what we're here for in the end. So can we image lipids of like mouse brain here? And the answer is yes, but not to a satisfactory degree, in my opinion. We see lipids in the lipid ray, like in this mass range. We see them, we can image some of them and get different spatial information, but these images will not give you a lot of detail because we lack ion yield. We don't have a lot of ion yield, we also see a lot of fragmentation and so on, and this kind of makes this technique perform under its potential right now. And if you look into literature, whenever people have tried multi-mass microscopy on this instrument of tissues, this has failed, also with other groups. So we have to talk more about this. Where does this come from? How can we solve this? And I think there are 2 primary reasons here. First of all, I still believe surface charging is bad for our ion yield. But another more fundamental thing we need to consider is that we do MOLDI at high vacuum. And most modern MOLDI instruments, they do MOLDI at ambient pressure or elevated pressure. And at high vacuum, you have fewer gas phase collisions in your MOLDI plume, which means you have fewer charge transfer reactions, you ionize less under high vacuum. It also means that you cannot collisionally cool hot molecules that would otherwise fragment. So we are inherently different in that regard, and that's a limitation. I believe for now what would work best is to look at pre-charged, very stable molecules that you just need to desorb that already carry a charge. I think this would work best, and ignore all gas phase effects that could possibly be there. That again would point us down the road for targeted MOLDI applications like MOLDI IHC, where you look at peptides that are labeled to antibodies, with which you look at many proteins at the same time, many more than were possible with immunofluorescence. You could also think about designing tags with LDI alone that would work even better. Okay, this kind of wraps up the mass microscopy research I did in my PhD, and I still would like to talk about a different topic I did with a colleague of mine, and my colleague wants to study interactions of microplastic particles with biological tissues, for instance, the marine environment. The reason is we find microplastics everywhere, in fish, basically also in the human body, but we don't know what the hell they're doing there. Are they toxic? Are they cancerogenic? And so on. We want to study this, but most polymers that form microplastics that do not ionize well with MOLDI, they're mostly insoluble. And we wanted to enhance the ionization, and for that we wanted to look at whether MOLDI-2 can enhance the ionization efficiency of polymers. And MOLDI-2, for those unaware, like MOLDI, you shoot with a laser on your surface, you have matrix crystals, you desorb in a plume. The idea behind MOLDI-2 is, okay, I take a second laser, normally 266 nanometers, and I intersect at this plume in a certain pressure region. What then is expected, well, it's the theory, it's not fully proven yet to happen, is that molecules that absorb at the wavelength of this second laser That's predominantly the matrix molecules. They get ionized via resonance-enhanced multiphoton ionization and form radical ions, and then you have two subsequent chemical reactions that lead to an increase in protonate species. In the literature, that's an increase by up to 3 orders of magnitude. So we thought maybe we'll give this a try. We tried polyethylene glycol first, which already ionizes well with MOLDI, and results first, they were not as good as we wanted to. So you see these spectra, they are fairly similar. All of these large peaks are salt adducts, and the ones annotated with the circle are protonated species. So yes, we increased them, but only by an order of magnitude. Salt adducts still dominate, and I would argue that this is of only limited use. However, we realized we could also use the source for a different application. That is, if we have a polymer that absorbs at this wavelength directly, to just do this first step, RAMP, which is highly efficient. And polystyrene is a good candidate for that. On the spectrum, with polystyrene, it looks like this. You don't see anything with MOLDI. Polystyrene almost doesn't ionize there. And with the second laser, with a mold RAMP mechanism, we get a very nice polymer distribution of radical ions. And I think this is a very significant result because polystyrene is exactly one of these long-lasting microplastic particles you can find in marine environments. And yeah, I hope this helps my colleague. And with that, I'm already wrapping up. So I hope I could give a short overview of why throughput is important in mass spec imaging, and that mass microscopy is now all of a sudden very viable again with the Timex 3. I believe mass resolution is going to be the Achilles heel of this technique, but we're making good progress, and I think we're already approaching a plateau of productivity when it comes to elemental analysis. With MOLDI, we are still a bit further out, but we made good progress in the understanding, and my hope is that one day we will be able to put mass microscopes in the clinic and make a difference with patients. Okay, with all this, I think I still have to acknowledge a lot of people, probably more than fit onto the slide. A lot more, and also companies for all their dedication and collaborative effort. It was a great pleasure and a privilege to work with them. And of course, I have to thank everyone here for their attention. Thank you.
Yeah, you may applaud. Thank you, Mr. Körber, for this clear overview, very complete. I think it was mainly meant for your colleagues who are, some of which are present here. Thank you for that. Your supervisory team has selected a number of experts to assess the quality of your thesis, and the quality of your thesis was assessed as very positive. So that's why you're now here to defend your thesis, and we are looking forward to see you answering the questions that have remained from your work in an academic fashion. And that is why Professor van Rijt will now open the opposition. She's a professor of inorganic nanomaterials for regenerative medicine at the Merlin Institute at this university. Please.
Thank you, Pro-Rector. Dear candidate, first, I would like to congratulate you on this great work that you present here today. And also, I would like to extend my congratulations to the supervisory team. But I also would like to ask you some questions. And my first question is actually a bit broader. So I'm not a specialist in mass spectrometry. So I'd like to start with a high-level question to help place your work in a broader context. So explaining this to someone outside the field of mass spectrometry imaging, what would you say is the core problem that your thesis addresses, and what is the key contribution you make towards solving it?
Highly esteemed opponent, thank you for this question. The core problem of this thesis is the technology development of an emerging imaging technique that mainly is just too slow to be used in a hospital.
Okay. And then if you expand a bit further, how do you see what key contributions would still be needed to actually use this technique in the hospital?
Basically, you have to enhance the measuring speed while maintaining sufficiently high spatial resolving power and sensitivity.
Yeah. Okay, so that kind of links to your chapter 3, right? So I would like to now focus on that, where you demonstrate a substantial increase in imaging speed. I would like to go a bit beyond the performance numbers and focus more on understanding why this approach is useful in practice, not just that it's fast. And focusing on figure 3.5 on page 90, here you kind of could you perhaps start with summarizing what this figure best illustrates about the strengths of your approach?
Yes, so I can also show this on the slide.
For sure.
Desired. No, 1 second. So the opponent speaks about the rat brain that we show on the right. Well, we show that we can use this approach not only in fingerprints and inorganic samples, but also on real biological tissue, which is a rat brain. We wanted to also demonstrate that we can look at different chemicals. The thing with SIMS is you can very easily look at sodium and potassium, but that is not what we are after in the end. So we went slower to get also signals that don't give such a high ion yield, like this image here of cholesterol. We really wanted to also capture this or some molecule here, which is very dark. This also shows that if your sensitivity is not good enough, you cannot image it. And so sensitivity is something that's limiting in this technique. And yeah, we also, again, we wanted to show the zoom-ins to show that you really have very nice spatial detail, which is needed because pathologists, they want to see individual cells in the tissue and know what they're doing, ideally.
Yeah, thank you. Actually, the part about sensitivity is where I wanted to ask you further questions on, because it seems from what you showed that there's a trade-off between sensitivity and speed. And you also explained that in your presentation. So could you perhaps elaborate for when would you decide to go for either sensitivity or speed, and give some examples of biological samples where you would choose either speed or sensitivity?
Well, it depends on what you look at. If you know what you're looking for, a specific chemical, and this shows, thanks to your sample preparation, outstanding sensitivity, you can go very fast. But if you do not know what you're looking for, and if these chemicals might be at low sensitivity or not prone to ionization, then I would go very slow. And also, I mean, the thing with SIMS is the higher you go in the mass of the molecule you want to look at, the slower you should probably go, because the fewer ions you will get per shot.
Yeah. And in your presentation, you showed some ideas of how you could improve the system. Would you then still have this trade-off between sensitivity and speed?
Yes, I think you will always have this trade-off.
Okay. I would like to move on to chapter 6. So as a material scientist, I found this particularly interesting because you observe clearly different ionization behavior for the different polymer classes that you research. So between MALDI and MALDI2. So based on your results, could you explain how you interpret these differences, for example, between polyethers, nylon, and polystyrene in terms of their ionization pathways in MALDI2?
Okay, so polystyrene does not undergo MALDI2. As far as we understand it, MALDI2 consists, so the theory, of multiple steps. The first one is called resonance-enhanced multiphoton ionization. The way this works is your molecule absorbs at the wavelength of your laser and it goes to a higher excited state. And this excited state, since the molecule absorbs, has a reasonably high lifetime to make it sufficiently probable that a second photon is absorbed and then the molecule ionizes. That is REMP. And I can also go back to this in just a second. The thing is, so this first step, that is REMP. You form a radical cation, and a radical cation is not always stable in a MALDI plume where you have high molecular density in the plume. You have a lot of collisions. What can happen is that this radical cation sees another molecule, maybe a matrix molecule, and forms a protonated ion. And the issue is with MALDI matrices in positive polarity, they are acids. So if you give an acid a proton, it will be very unstable, so it will transfer the proton to the first best molecule it can find. And this is the MALDI2 mechanism as proposed. This is what we do with the for instance, with polyethylene glycol. The idea with polystyrene is simply that polystyrene absorbs at the wavelength of the second laser, and we just do this first step. We ignore the others.
Okay, thanks. I have one final question, but please stay brief. So in your rationale for the chapter 6 is that you want to investigate micro and nanoparticles, but then if I look at your sample preparation, you spray coat from solution, so these then presumably don't form micro or nanoparticles. Would you expect the ionization behavior or the analysis to change if you would really analyze particles instead of tried solutions?
No, the behavior would not change. We did this with standards because we first wanted to understand on a fundamental level what is happening. And the issue with microplastic particles in tissues is you don't have a lot of material you can desorb and ionize. And for a fundamental study, we thought it's better to start just with the pure polymer and see what's happening. But we would expect very similar behavior.
Okay, thank you, candidate. I give the word back to the pro-rector.
Thank you, Professor Van Rijt. The opposition will be continued by Professor Makarov. Professor Makarov is Scientific Director of the High Resolution Mass Spectrometry Institute of Thermo Fisher Scientific in Bremen. Welcome. Professor Makarov is present online. The floor is yours.
Good morning, dear candidate. I would like to congratulate you with this nice work. And we all know that technology development is a really tough business. And as mass microscopy is the core focus of your thesis, you mentioned that its Achilles heel is insufficient mass resolution. How do you think this could be handled in the future?
Highly esteemed opponent, thank you for the question. The thing with mass resolution is there are multiple factors that can be bad for your mass resolution. One is the behavior of the ion gun you use in SIMS. In MALDI, this is a different story, but basically the ion gun can emit a pulse of a width that you define. This can be bad for your mass resolution if this pulse is very broad, and we used for broad pulses in the beginning to compensate for bad sensitivity. One thing there is that our ion gun is not designed for short pulses, and what people then do, it's something called bunching. We use two electric fields to just compress your ion gun pulse. We cannot effectively do this in our ion gun because you need two ion optics, well, one in front and one behind the pulse to do this. We only have one of these. But basically for SIMS, what would be very good is if you could bunch your ion gun. With MALDI, it's different. You get a very broad kinetic energy distribution of your ions, which is inherently bad for your mass resolution. Normal MALDI instruments that do delayed extraction, I know you're familiar with that. Delayed extraction is not possible with MALDI mass microscopy because you lose the image information. A separate technique named post-extraction delayed acceleration exists, named PETA, which one could investigate, but maybe not on a sector-based instrument. I mean, basically what this does is it increases the sample potential after a short delay to accelerate ions at the back of the pulse. So this is on the ionization side. On the detector side, yeah, I mean, the DMCP, I would say, has very good time resolution. The Timepics 3 will be superseded by the Timepics 4, which has about 200 picosecond time resolution. This will already be better. But I think the main thing will be the scintillator. Because of its rise in decay time, we cannot get rid of the decay time. You can also consider using a Timepics in vacuum directly behind an MCP, but that runs into a completely different set of issues.
And what about mass analyzer? Is there potential there to improve performance?
I would say not yet. Yes, I mean, you're obviously right. The mass analyzer in the end determines the mass resolution. But over the past 20 to 30 years, other factors, mainly the detector, were limiting. So even if I built a mass analyzer with amazing time resolution, if the detector isn't good enough, you can't do it. So with the mass analyzer, once we optimize the detector with the scintillator and maybe the Timepics 4, yes, one could consider building better mass spectrometers. There exists several suggestions, like one from John Heuss and Anatoly Verenchikov, to build a stigmatic multi-reflectron mass microscope. But we have to see how realistic this is. But yeah, of course, you're right. The mass analyzer plays a good role.
And you mentioned the importance of a scintillator. So why was the Cryo 60 scintillator screen from Cryoture chosen over other available scintillator options?
The thing is, there was not a lot of literature. We did not know what was existing. We looked briefly at organic scintillators, but we were concerned about their stability, especially under high vacuum. And the thing is, there are a lot of scintillators in the literature that are very fast, but they're unsuited because of a different wavelength regime in which they emit light and so on. And basically, at some point, we just approached several manufacturers and asked what they could do, and then Kreiter offered us a collaboration.
Okay. Now I wanted to ask about your chapter 2, the literature review. So why nanodesi was considered to be out of scope for this review? This technology actually delivered some spectacular progress with protein imaging in the recent years.
Yeah, well, the thing with nanodesi is we discussed this heavily multiple times, and then 2 people out of 3 decided not to. And since this was brought, I brought up in your written feedback, I brought some slides why I don't believe in nanodesi. So, I mean, you're aware that DESI, which sprays droplets onto a surface, and nanodesi are completely different things. Nanodesi means you pump solvent onto a sample, you form a liquid microjunction, which is just a droplet, and then you dissolve stuff from your sample and you suck it in again. And this comes with a few issues, and the thing is, like, in all of mass spec imaging, we really try not to get chemical delocalization. And now you pump solvent down and you move over a surface, so you will smear out all the signals you get. The next thing that's also linked to that is that it claims to have a spatial resolution of 10 to 12 micrometer, which it just doesn't. Like, this is how they showed it in one paper. It's always cited with a rhodamine grid on a plastic surface where the solvent doesn't interact well. But this is what the tissue looks like. Like, this is a 1,000 micrometer scale bar, and you can't see anything. You see smeared out things. You cannot look at holes between a tissue that are much larger than 10 micrometer. And it is suggested that this has this resolution, but there's, in my opinion, no good evidence on that it has a good resolution.
Mr. Körber, cannot see your slides. If you're showing slides, we cannot see them.
No, I see you.
Oh, you can see
Alexander
them.
can see
Okay,
them. Okay, then
thank you.
So there's no evidence for high resolution. I would say it's more like, it's worse than DESI in spatial resolution nowadays. Other issues are you have a lot of black lines because your capillaries clog quote all the time. According to Julia Laskin, that also means you cannot accurately locate what you're looking at. So it is the only technology that I know where the spatial resolution reported has gone down over the years without any changes to the instrumentation. And the thing is, I believe you were referring to nanodesi imaging of folded proteins. And I think this is interesting, but it won't be useful to the main people in the community. And the reason for that is whether you do DESI, MALDI, or anything without separation step, you will only ionize and see the most abundant proteins that ionize well. And so, I mean, what Ollie Hale looked at was several globins, fatty acid binding proteins, and so on. And these are not, in my opinion, the most interesting ones. The image quality still is really, really poor. And the question is then, what is it all good for if you look at alternatives? Given poor spatial resolution, what you could do is you could just do laser capture microdissection, cut out things of the tissue and analyze this with a chromatography and get much better data, whether you do native MS or bottom-up proteomics. You could do imaging mass spectrometry if you're just interested in the proteins, or very heretical from my point of view, you could just do MALDI with auto-folding information, because I have to ask, what is the added value of seeing folded protein information if my spatial resolution is bad and if I only see the most abundant proteins that we already know very well? So what do you intend to do?
Sorry to interrupt again, but for the sake of time,
I'll finish the sentence. Yeah. If you want to look at proteoforms, you have to see all of these proteoforms with sufficient sensitivity. You need a sufficient dynamic range. So I think nanodesi is not going to have a very good future. It's done by 3 groups in the world, so I decided it's not important to the reader.
Thank you very much for such an impressive answer.
Yeah.
Thank you.
Thank you, Professor Makarov. Then the opposition will be continued by Professor Hild. He's a professor of gravitational waves and fundamental physics at this university.
Yeah, thank you. Dear candidate, let me continue or pick up again to congratulate you on the thesis. I think I enjoyed the reading very, very much. It was an impressive work, and I really like this kind of combination of fundamental kind of measurement techniques to the application. And coming from particle physics background, it's very happy to see that the MEDPICS is not only used in CERN, but actually, might end up in our hospitals. I would like to ask a few questions on these measurement principles, and I would like to start with figure 2.12, where you mention kind of, so this is regarding the ion mobility spectrometry, and there you see, or you mention ions are periodically confined and pushed forward by periodic DC waves. Mm-hmm. And for me, DC always means something static or 0 hertz. Waves obviously imply something which is oscillating, has a frequency. So I was just wondering whether you can clarify which parts here are actually static and what is the oscillation which causes the waves.
A highly esteemed opponent, thank you for this question. Yeah, I think I get the confusion. I think I agree that this is a bad formulation. The thing is, you have a wave when, basically one could consider this to be then not a DC potential. Yeah.
I'm not arguing with the formulation. It's really kind of just to understand what is oscillating and in this image here.
I mean, basically, you have your ions. They're confined by outer ion optics, and then you have periodically coming electric signals, and that push it forward against the gas. So,
okay, so it's like a standing wave which then moves over time. Is that more or less the image there? Okay, good. Okay, I think, as I said, the formulation is not just tripping you up, but I don't think it's necessary.
No, it just confused me as well. I wrote this a long time ago.
Okay, very good. Then another thing I was wondering a little bit about that relates to figure 4.3, where you show kind of, making a nice analysis of your achieved pulse width versus your ion gun pulse width. And you see there these different numbers like 9, 14, 30 nanoseconds, 80 nanoseconds. And then the pulses are obviously longer, but are 40, 100, 120, 160 nanoseconds. So there's apparently something nonlinear going on here because this doesn't relate to. So where does this nonlinearity come from? And how can you use it to your advantage?
First, to explain where this nonlinearity comes from, like this 40, 100, 120, and 160 nanoseconds is something you enter basically on a software that controls the ion gun. And what this pulsar does is it has a potential that normally deflects all ions against the wall, and then it shortly lowers this potential. So first of all, I would expect that to be nonlinear because this potential needs to go down, and I don't think they use very, very fast electrical components there. Then the different thing is the time of flight spectrometer that we use does a partial compensation, so we don't know what it does with whether it shortens the pulses that they emit. And I think, what was the second part of your question?
Whether there's anything you can make use of it now that you measure there's something nonlinear. Is there anything where you can optimize it, find a sweet spot or something, or whether this is just given and you work with it?
I'm afraid it's rather the latter. I mean, maybe theoretically, if you really optimize the electrical components you're using in this ion gun, but that's probably a PhD thesis for itself. So, and I need funding, and I know who's going to say no to that.
Fair point. We'll not argue with that. Very good. Maybe I can ask one final question, which relates to the optics part, where you use a laser in, for example, figure 5.1, where you say a Gaussian laser beam is homogenized in a multimode fiber. So what exactly is homogenized there? Usually, I mean, I come from a field where we do everything with single mode fibers. To get a single mode out there, you say, oh, my advantage is to pump it or to get it into a multimode. So what do you harmonize in there?
A multimode fiber compared to a single mode fiber has a much broader core, and light can travel through it in different ways, which physicists can calculate and call modes. But for instance, you can think about a helical path, you can think about a zigzag through the center, and then you can have a different angle. And basically, light that travels through differently, these modes, they have a different, beam profile. And if you mix the right ones together, you can get a flat top, you can also get a donut, and then there are some people in Australia that can get all sorts of letters through. It's different ways of reflecting light via total internal reflection, basically.
Okay, then final brief question on that, maybe with a brief answer. So you get this kind of flat top out. Is that by chance? Is that by magic? Does it depend on your 10-meter length? Would you, if your fiber would have 1 meter, would you get it? Is that by chance, or is there something you actively do to get the flat top?
No, it's not by chance. I mean, the thing is, it's a little bit of an art. So first of all, yes, a longer fiber helps. A larger core size helps. And then, you need to get the right modes. So you want to bend the fiber in a way that reinforces one mode versus the other. And it's basically trial and error with a beam profiler.
Okay, thank you. Thanks very much for the insightful answers. I hand the word back to the chair.
Thank you, Professor Hild. Position will be continued by Professor Omens. He is a professor of molecular structure and dynamics at Radboud University in Nijmegen. The floor is yours.
Thank you very much, Mr. Prorector, and congratulations also from Nijmegen for a wonderful thesis. I would say it's very impressive technologically, this microscope mode mass spectrometry and the time gain that you achieved there. But I would like to ask you a few questions about another chapter in your thesis, and that's chapter 6. On where you implement MALDI-2 and you try to understand at least how it works and why it improves the ion signal in some cases, but in other cases not. And you use in your experiment a number of different polymers. I noticed that one of them, the nylon, you see different results for the nylon, but the nylon polymer is much, much longer than all the other ones. So I was starting to think about, could there also be multiply charged species for, the polymers have molecular weights of 25,000. And in that sense, your objective is that more molecules pick up a proton in your MALDI-2, but it could maybe also be the case that a single molecule picks up more than one proton. Is that, and especially for the very long ones, so for the nylon sample, is that something that you considered?
I don't think that in our experiment we've ever seen multiply charged ions. Yeah. I don't think we also put a large focus on that. The thing with nylon is it was not ionizing well, and we focused on other polymers. Other than that, I don't have much knowledge of any MALDI experiment that gives you multiply charged ions. And with MALDI-2, I mean, maybe Jens knows this.
Yeah, but maybe...
I don't know whether there's ever been any indication that you get multiply.
No, I see that from your, if I look at figure 6.2, the panel with nylon 6 there, that's clearly singly charged. But then the mass that you see is much lower than the mass of 25,000. So the top right panel in figure 6.2.
Yes. The figure 25,000 is the distribution of the polymer.
Yeah.
Which means you see much heavier and much more lightweight ions.
But 793 is very much smaller than 25,000.
Yeah. Again, the nylon 6 did not ionize very well. And another question is, okay.
I'm a bit surprised then, because if I look at the structure of nylon, is pretty basic, I would suppose. It's very long, so it...
No, I mean, first thing I still wanted to say is we're using a QTOF, and the QTOF, the quadrupole has a mass range that it allows.
Yeah.
25,000.
Well, this was my next question. Maybe the sample was not so well chosen in the sense that it's far outside the mass range of your mass spec if you ionize only, with one charge. Is that?
It depends on what you want to see. I mean, we wanted to see nylon. We wanted to see whether switching a second laser on changes something. I mean, this is where we succeeded. We don't see the 25,000 on this instrument at least. We could see it on an axial reflectron TOF. Yeah, I mean, the goal was to just see whether you see a change, not to look at very high masses. And just another thing you said with the ionization of nylon, the trouble we had was dissolving it. And also, if you think about matrix application, what you have is when you spray that or sublimate, you have some sort of liquid extraction step. and that then mixes with the moldy matrix and co-crystallizes, but if it doesn't dissolve, it will not co-crystallize, and then you won't see it. So that's what I think made it very difficult.
So that's maybe the nylon experiment didn't work so well in the end. That's
I would agree, yes.
Yeah. Another statement that you make, it's on page 146, I found a bit remarkable statement for a chemist. You say thermodynamics are unlikely to have strong influence. That's what not many chemists would say, I think. Thermodynamics usually determine almost everything in chemistry, together with kinetics. And also in this case, I would say the proton affinity determines your ionization efficiency, and so that I would say is thermodynamics. So is that not?
No, I don't agree with this. The thing with thermodynamics is mostly defined for equilibrium, like standard conditions, a solution, and that's where thermodynamics really shines. But a moldy plume is a lot of a very hot, fast-moving molecule with a lot of excess energy that just got ripped out of a crystal. So the thing is, thermodynamics normally is governed by trying to minimize the energy in your system. But every molecule here runs around with an excess of energy.
Yeah.
So if everyone's rich, everyone will have a Porsche. That then capitalism doesn't work anymore.
But then another statement, that's the first sentence on the next page. You say, the observed polymer ion distribution might not accurately reflect the polymer distribution. And that I agree with, because that's exactly an effect of higher or lower proton affinities, I would say. A longer polymer has a higher proton affinity and so gets ionized more efficiently. That's more or less the statement you make on the top of page 147.
Yes, on that. First of all, there has been a study by a former colleague of mine where they looked at molecules with different proton affinities to check whether there's a correlation in a molecule.
Yeah.
Expectation was that molecules with higher proton affinity should ionize better. That was not confirmed. That is one thing to know.
I'm surprised. Why would that not be?
Again, proton affinity is a thermodynamic quantity defined for equilibrium. And we have a very hot moldy plume here. And
but what defines then the ionization efficiency?
Our investigation into this remained inconclusive. We considered a number of factors next to thermodynamics. So kinetics, you mentioned that already. For instance, we were thinking, okay, if a molecule is lighter, it might be faster and it might increase its probability for collisions. We were considering the probability of desorption because we know the weight distribution according to manufacturer, how it is in solution. But if you take a polymer, still the lighter weight molecules will desorb more easily. This could be a role. And then there are other things like what's happening in a moldy plume, like because we're shooting at a part of the moldy plume, but we don't know what's happening at this part, whether we selected the right part, so to speak. So it could be that different weights are at different parts in the moldy plume. This is just hypothesis. We don't know what's going on. And I mean, in the end, we wrote a discussion on that and said our findings remained inconclusive.
Yeah. I think the pro-rector was looking at me. That means the time is up. Thank you very much.
Thank you, Professor Omens. The opposition will be continued by Dr. Soltwich. He's an expert in biomedical mass spectrometry at the University of Münster, Germany.
Yes, also congratulations from my side. Mr. Candidate, very nice thesis. I would like to start with sort of comparing the two sides of your thesis. So in one part you use MALDI-2 to increase ionization efficiency, and in the other part you use microscope mode, where that, and you described that very nicely, doesn't work. So would you have any wild ideas on how to increase ionization efficiency in microscope mode, where you can't do anything with the plume afterwards, obviously?
Highly esteemed opponent, thank you for your question. Increasing ionization efficiency, I think you will gain most by forming these ions already on the surface, and indeed not in a moldy plume, because we don't have as much of a moldy plume, and even if there was gas phase ionization, it would not be helpful because it would not have the spatial information. I considered drastically increasing the acidity of my matrix, but that didn't help. So this is something I considered. Other than that, I would say it's a good question. Like, I don't have a good recipe for that, no.
Okay, and maybe in that same direction. So you described the spot size effect for multi. So if we move away from SIMS and just look at multi, you described the spot size effect where you need a lot more energy per area with small spots as compared to large spots. And that goes hand in hand with differences in starting velocities and speeds and stuff. So would you think that that there could be a sweet spot of sort of spot size you need for microscope mode, or is it always better to go to very large spots? And yeah, maybe answer that first and then continue with another question.
Yeah, I had some hopes on the spot size effect, but it did not give me a lot of difference. Sort of the spot size effect in multi-mass microscopy in general, I think you will always try to get a large spot in a large field of view because we want high throughput, and the larger my field of view, the faster I can go. So I don't think people will be too willing to look at trade-offs. Another thing I was a bit concerned about is my laser spot is larger than the field of view of my ion optics, and the reason for that is that I was not sure whether ions on the edge of the spot experience the same field as in the center. Like, I was considering scenarios in which you charge up to the left, let's say, of an ion, but not to the right, and then this ion will just get kicked out of the focal point of the ion optics. So okay. I don't think I want a smaller pole.
So would you expect if you take a microscope mode measurement of a sample and then at 100 micron, let's say, spot size, or if you raster the same sample with 5 micron spot size in microprobe mode, would you expect to get the same spectra? Like thinking that you have a perfect mass spectrometer then with the same resolution and throughput?
Well, depends on the laser fluence, like the spot size effect dictates that you need higher ones.
At optimized conditions.
Okay, so you want to compare a mass microscope with a microprobe mode, then the question is pressure regime, because if one is elevated pressure, then again you will ionize better and more.
I would argue that even at let's say Repiflex at high vacuum, there would be differences from a small spot towards a large spot, especially also with starting velocity. So would you think that maybe there is a advantage of using smaller spots and then just doing a smaller mosaic as opposed to very large spots? Or would you think that, or do you think that could change anything if you go from 100 to, let's say, 15 or 20 micron spot size?
I don't have a mental model in my head that would lead to a mechanism. You maybe know more than I do in this regard.
All good.
And yeah, I would say it's something you would have to try.
Okay. Maybe another question also concerning microscope mode. You mentioned in your thesis that that it's very that you can look at different sample heights. For example, if you put that grid on top. Would you think that these differences in height play a role, or I was sort of surprised that these differences in height don't introduce changes in the calibration or the mass resolving power? Is that, or is that just something?
Well, they do, but on mass resolution is too bad to see it. So the thing is, there's a paper from I think 2003 by Leah McDonnell where they just used an ADC from the MCP, and they saw that peaks at different heights have a slight peak shift, and he used this to essentially map the entire topography of the sample. And I've always wanted to do that, but for that we need better mass resolution. But yeah, then it would be a 3D method. Okay, then maybe the last question. On that polymer chapter, you say that most of the increase in sensitivity you get if you get direct Rampey of these samples, which I agree with. Would you have you experienced or seen any UV-PD, so dissociation of these samples induced by the laser? So I mean, the upside is they absorb, so you ionize them well. On the downside, they absorb and they might just fall apart and fragment based on the laser. Yes, we've seen some indication. If you go to page 152, polystyrene is normally done with a silver cationizing agent like a silver salt added. And we also compared measurements with the second lasers versus measurements without the second laser. And for instance, we saw that the amount of silver added ions decreased. And this points, in my opinion, towards the fact that maybe these polystyrenes, either they're ionized again and somehow get rid of the silver, or maybe they are fragmenting. So it could be that there is a UVPD effect as a trade-off, yes.
Okay, thanks a lot, and give back the...
Thank you, Dr. Soltwich. Then the opposition will be continued by Professor Van Rooij, and he will also finalize the opposition.
Thank you, Mr. Pro-Rector. Dear promovendus, nice thesis. If I look at it from a distance, I see that you start enthusiastically with your Timepics camera, but then going to the end of the thesis, it seems that this Timepics camera fades away. Oh, you look surprised. So it's my interpretation that maybe the Timepics camera was not addressing the main bottleneck in speed is a wrong interpretation?
Highly esteemed opponent. Yeah, I'm surprised I cannot follow your trail of thoughts at the moment.
Yeah, but
So
if I look at it, I think the Timepics camera, throw that away, spend your effort at something else.
well, the Timepics, well, I would say that's not accurate. I mean, we did a lot of work on the data processing, which is part of the Timepics 3 camera. And the thing is, like, the first chapter is indeed we introduced the Timepics 3 to mass spectrometry imaging. And well, since then it worked. So it was not the limiting factor. And then we looked at other things like the scintillator performance, like the ionization. But the Timepics 3 has always been a crucial piece in this research.
Yeah? Because if I look at your Timepics camera, you hardly turn it on. Huh? Only one pixel is doing a job at a time, and only for a nanosecond, or do I get it completely wrong? So I would think I would have invested in 30 lasers and put much more power on the sample, or do I oversee something there?
Yeah, the thing is, I'm confused. The thing is, the Timepics 3, it's a 256 by 256 chip, and we try to irradiate as many chips as possible by first having the magnified ion image on the MCP and then using a zoom lens to magnify this image further. So the Timepics, I would say, is very busy, and we, of course, use way much more than 1 pixel. So I'm confused.
Yeah, but maybe I was misled by your presentation, because there I see still you saw a ion beam scanning still over the sample, right?
Okay, that explains it. Yeah, so the thing with the mass microscope is our instrument, other instruments vary, is we have a field of view of maybe 200 by 200 micrometers. And images that are several millimeters large, we still want to scan. So yes, we move around, but we are looking at images, not just single pixels. So everywhere we move, we see a 200 micrometer field of view, and we add these 200 micrometer field of views. Microprobe mode, they really just see a pixel and they add up individual pixels. But in our field of view, I mean, with 256 times 256, you have maybe 60,000 pixels on a Timepics. I mean, so yeah,
You still like the Timepics?
Huh?
You still like the Timepics?
Good.
Let it go.
Starting at it, but
Let's also do some science. I saw some plasma in here. I saw ionization. I like that very much. Can we quickly move to figure 5.4? Because there I'm a bit puzzled. There you sketch an ionization threshold. What's on the y-axis?
This is a schematic drawing that shows a Gaussian versus a flat top laser beam. The y-axis in this case would just be the intensity of the laser beam.
So that means somehow you are looking here at a multiphoton process, otherwise.
No, you just measure the fluence of the laser beam, and its maximum in the center.
Yeah, but yeah, I'm misguided by ionization threshold. I think then it's in electron volts or so, not in intensity.
No, this is again a schematic drawing, and it's to discuss the advantages and disadvantages of Gaussian versus flat top laser beams, specifically for MALDI. And MALDI has an ionization threshold, and that is just the laser power you're shooting at your sample. You first don't see anything, then at some point you start desorbing, but you do not ionize. Then you ionize, and then you can go further, but then you will start fragmenting a lot. And modern experiments, they try to get the sweet spot of being at the threshold so that you ionize but not being above. And if you take a Gaussian laser beam, it's not homogeneous. So either you only have the tip of your beam be at the ionization threshold and then you do not ionize much, or if your Gaussian beam looks like this and your threshold is here, a certain part of the beam is just going to be above that, and that will lead to fragmentation and surface charging. This is what this drawing is telling you, or supposed to.
Yeah. No, so is then the ionization happening still within the time duration of the MALDI laser shot?
That's a question. The ionization in MALDI, that's an entirely different process that's been subject to a lot of debate in the literature. So what you do when shooting at the MALDI matrix, you release a lot of material into your chamber. And the ionization, there are two models suggested for that. One is that these hot clusters, that they just decompose, they cool themselves by evaporating molecules, and then you have a lucky survivor ion. That would be after the laser pulse, obviously. And the second thing is you have collisions in your MALDI plume, and that leads to ionization. It's also happening after the duration of the laser shot.
Yeah, so maybe I'm wrong, but I was searching here for plasma, and I was hoping that the plasma plume from MALDI creates ionization. And then,
Okay, I was referring to the molecules. Like, if you form a plasma, weakly ionized plasma, then you have already ions. I was referring more about the mechanism. So yes, this weakly ionized plasma, it contains ions, yes.
Yeah, I was misjudging the time. Also quickly about the synthetic polymers. I was very much surprised by the irregularities in the molecular weight distributions. Are you surprised by that? For example, in figure, we have to be quick now, 6.1.
1 second.
There you see all these peaks alternating. How can that be?
Peaks alternating, could you?
Yeah, in the lower part, in the blue part, I see at 1400 a very strong peak, then one that is less strong, and the next one is stronger again.
I see. This could have multiple reasons. It could be that there's a variation in the standard, which I don't believe. It could be that some desorb easier, which I also don't believe. In this case, it could be that this is just an uncertainty of your measurement in your mass spectrometer. It could be that this is just an intensity difference when you shoot with MALDI, that you would get this distribution if you had better statistics.
You can briefly finish your answer if you want to.
I think I have.
Okay.
Thank you very much.
Thank you, Professor Van Rooij. Mr. Körber, the time appointed for defending your thesis has passed. The degree committee will now withdraw and discuss the quality of your thesis and the quality of your defense. I request that you and your company await the result of a deliberation and our return to this room in here. Mr. Körber. The degree committee here present has assessed the quality of your thesis and the quality of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Heren is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Aljoscha Körber, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee and affixed with the official seal of the university. Dear Dr. Körber, dear Aljoscha, congratulations. Congratulations on your newly obtained honor as a Doctor of Science. A title that fits you like a glove, as I've gotten to know you over the last 5 eventful years as a true scientist that is wary of compromise and prefers science to be exact. Not debatable, as in some fields of science, but truly exact in the sense that there are only 2 right answers. The right one and the wrong one. That, combined with your outstanding debating skills and an eidetic memory, has resulted in a remarkable journey that has culminated in your very well-deserved success today. Let's go back to the beginning. You started in August 2020, still in the middle of the fallout of the COVID-19 pandemic, and your enthusiasm and intellect during your interview were contagious. And it was clear already then that you were unlike any other PhD student recruited to M4I. Very well prepared, aware what had been done in our institute in stigmatic imaging, and interested in combining electron microscopy and mass spectrometry in the NAMI project that we just got funded. Not the easiest time to start, as became abundantly clear when the NAMI project was delayed and delayed and delayed and delayed again due to legal issues, the inability of service engineers to come to Maastricht due to COVID-imposed travel bans, and a very late delivery of the base instruments, resulting ultimately in the shift of your intended research during your PhD, as we've heard today. Already early on, it was clear that you were one of the most intelligent students that I've ever supervised. You exhibited an enormous body of knowledge and were one of the most critical thinkers I've ever worked with. In fact, I looked it up, and in your first year evaluation, when we were describing the competence of critical thinking, we had to make an additional box on the form to indicate how extremely good critical thinker you were. Your attitude towards science has always been one of your strong character traits that I really enjoyed working with. You started working together with Ian Anthony on the NAMI and the stigmatic imaging project on the biodrift with the Timepix-3, something that turned out to be one of the scientific highlights of your thesis that you very well defended today. You demonstrated that it was possible to measure an entire microscope slide in 30 minutes, 33 to be exact, sorry, I have to correct myself, with sub-micron resolution with SIMS, something that have never been shown before. It was the basis of a new way doing stigmatic imaging, and the analytical chemistry paper from 2022 has already been cited more than 30 times during your PhD. This project was further enhanced by your insatiable hunger for new knowledge in literature and your keen eye for new developments in the fields. and developments that maybe are not so useful, as we've heard in your defense as well. You've collaborated with several different companies throughout your PhD, and your collaboration with Crytor has forwarded the team's work on direct ion imaging. The new scintillator, described in Chapter 4, has improved the sensitivity needed for Timepeaks-3-based detection under atmospheric conditions. As a team player, you also realize that some of our collaborators, such as Jens Soltwich and Alexander Makarov on your committee here today, who I would like to thank for their participation in today's proceedings, were essential to forward our science. Science works in collaboration. Our joint projects with them are not yet fully completed, and I'm looking forward to continuing our collaborations. I also want to use this opportunity to express my gratitude to the entire PhD committee present here today for their candid discussions and constructive feedback leading up to Aljoscha's success today. Thank you very much. Aljoscha, you've also been there for your colleagues when they needed you. A good example is the work you did together with Lydia on MALDI-2 of the polymers. As a team, you dove into the explanation of the reasons behind ionization efficiency improvement or not on different polymeric systems. And we've extensively discussed that today as well. Your knowledge on fundamental physical chemical processes was pivotal to the explanation of the effects observed. It was a beautiful example in my mind how researchers with a very different backgrounds and interests can come together as a team to solve complex problems collaboratively. Throughout your PhD, you've also meticulously worked on an authoritative review that was finally published this year. It was a perfect example of your critical view of the innovations and developments going on in mass spec imaging. I predict that this review will be heavily cited in the months and years to come, as you've provided an outstanding state of the technology analysis, which is truly a new benchmark. Many of your successors at various stages of their careers will benefit from your perspective on imaging mass spectrometry. You are an amazing debater, as I said before, and I thoroughly enjoyed being challenged by your perspectives. My favorite moments were when you came into my office with a quick question that turned into a political discussion, and particularly local or geopolitical developments. There too, I was often confronted with your opinion that was both insightful and often confronting. But you achieved what I can only assume was your purpose. You made me think differently. I believe it has made me a sharper scientist, so I've learned a lot from our interactions, and I want to thank you for that. It remains important for all scientists to stay open for the perspective of others, as it might change your own. I hope this openness is something you will also take forward from this PhD journey onward. Not everything went as smoothly as we had hoped for. Whether it were COVID restrictions, health issues, instrument misbehaving, or accidental collisions in the naming instrument, or some of the other challenges you faced, you've always dealt with them in a way that defines you for who you are. No compromises. I also want to thank your co-promoter, Benjamin Balloff, who stepped in on your request to change supervisors. And while we have not always agreed on several matters, I'm very happy to celebrate your success with you today. You are definitely the most intellectual PhD student I've supervised so far. Some make it to professor, here. Some choose a career elsewhere. You are moving away from academics, exploring a career, perhaps in patent evaluation or patent development in a different environment, but the future is still open. I think that this is a career that fits all of your talents very well, and I wish you all the success in the world in finding an appropriate and suitable position. I want to end by congratulating you once again, and these congratulations are also intended to your family and friends, who probably are even prouder than I am that you are standing here now as Dr. Körber. Congratulations, Aljoscha.
Highly esteemed Dr. Körber, it is my great honor and pleasure to congratulate you on behalf of the University of Maastricht and the Board of Deans with the degree that you have just acquired. I would also, of course, like to congratulate your supervisory team, your family and friends, and also those that have collaborated with you and contributed to the chapters and the papers that have come out and will come out, I understand, in scientific journals. I saw several to be publications in preparation in your list, so I presume that those will be published in future. Your thesis was judged very positive. It describes, in my view, an important development in the techniques used in mass spectrometry imaging, important also for the further implementation of these techniques in the biomedical sciences. With respect to your defense, I witnessed an excellent defense. A lot has been said already. You were very well prepared, as evidenced by your slide, your PowerPoint presentation on one of the questions. You were calm and self-convinced, and your answers were very adequate, answers to a plethora of different questions. And it's obvious that from your thesis and from your defense that you have developed into an independent researcher with an analytical mind, but also conscientious of things that do not work, and you're honest about that. And I think that is a very important characteristic of a scientist. It has been said, and it was evident from this defense also, that you're an excellent debater. I would like to congratulate you again with your success, and wish you also further success in your hopefully scientific career. I mean, I think after having presented such a beautiful thesis, you have an obligation to continue in science. In what way? So good luck in finding a new position. I understand you're looking for one. And I also would like to congratulate everyone that is present here. As said, the collaborators in the chapters, and I presume several of those are here present. Before I end the ceremony, I have a question to the audience. I would like to ask you to leave the room after I finish the ceremony. Please already go to the rector for the reception. We will stay here for a minute to make a picture together with Professor Makarov in the back. And I would also like to give Professor Makarov a chance to congratulate you. And then we will go to the hallway, to the stair, and make some additional images. And having said this, I hereby end this ceremony.
I have to take this with me.
Kun je mij even de microfoon geven?